Hello everyone, we're going to start today's lesson by looking at the assignment from the book from yesterday. So you just had to do these 4 problems. So for number 31, we're given dy over dx, so we're given the first derivative. We want to come up with an equation for y that satisfies this initial condition of y of -1 is equal to 0. So if you could tell by looking at it, that's fine. If not, I just took the antiderivative of each term here. So for the first one, we get 9x cubed over 3, which simplifies to 3x cubed. Next, we get minus 4x squared over 2, which simplifies to negative 2x squared. And then plus a 5x and plus c. Then we go down to using the initial condition. So everywhere there's an x, we put in a -1, set it equal to 0 to find c. So it turns out that c is equal to 10. And then we just rewrite the equation for y, but instead of plus c at the end, we put our plus 10. Right, now for 34, we have to be a little clever here. dy over dt is equal to 1 over x. So anytime we're looking at the antiderivative of 1 over x, it's the natural log of the absolute value of x, and then in this case, plus c. Using the initial condition, we get 0 is equal to the natural log of e to the third plus c. And then using the laws of logarithms, we could bring that 3 down in front. So it's 3 times the natural log of e. Natural log of e is 1, so we just get left with 3 plus c, so c is -3. And then there's our equation, our specific solution. All right, for 43, it's asking us to draw a possible graph for the function f with the given. So anytime, and we're going to get into slope fields for sure, but this is an example of a slope field. We see all of these little sort of line segments indicating tangent lines. But to draw a specific curve here, meaning we have a specific solution, that initial condition is that f of 0 is going to equal 0. So draw a possible graph for the function f with a given slope field that satisfies the stated condition. So this means I need to put a point here. And that means my curve has to go through this. So these are, think of these as just guidelines. So I'm kind of following this track right here. Draw it a little better. We're looking like this. That's all we had to do for 43. I know it's a little bit tough to have to redraw the entire graph here with the slope fields. When we go over this, I'm going to definitely give you a handout that has them already drawn in there. All right, so for number 59, says suppose $1,200 is invested in an account that pays 6.25% interest compounded continuously. So that means we can either start with the a equals p times e to the rt function, or y of t is equal to c times e to the kt. Either way, you still have to state the initial formula that you're using before you substitute the values in. So for a, it says find a formula for the amount in the account at any time t. So in this case, I'm just using the second one. Y of t is going to equal 1200 times e to the 0.0625 times t. That's all we had to do for that. And part B is just finding how much time it takes for the amount to triple. So that means to go from 1200 to 3600. So in order to solve this, we first want to divide both sides by 1200. So that's where I'm getting the 3. In order to solve for this variable that's in the exponent, we take the natural log of each side. So this is our exact form, and then we approximate it, so about 17.6 years. All right, let's take a look at these 2 integrals that I asked you to evaluate here. For the first one, it's just sort of to try and check. So here's the thought process here. We know that the derivative of sine is going to give us cosine, so we would start with sine of 2x. But now if we were to take the derivative of this, we would get cosine of 2x times 2. So then we have to get rid of that extra times 2, so we would put a 1/2 out in front. So that's where we're coming up with that, and then the plus c. And then very similar for this next one, we could start by leaving the 4 there. Now, the derivative of negative cosine would give us sine, so I'm going to put times, and we'll put a negative, I'll leave some space here, cosine of 2x. And then just like up here, we would need a 1/2 out in front of it, and then our plus c. So then just multiplying 4 times negative 1/2, there's our -2 cosine of 2x plus c. All right, let's take a look at the 2 AP practice problems from pages 38 and 39. All right, so for 25, the question is for which pair of functions f of x and g of x below will the limit as x approaches infinity of f of x over g of x equals 0? Well, this is going to happen anytime our denominator is larger than our numerator. So for a fraction, as x keeps increasing, that means we want our denominator to be much larger than our numerator because we're going to get a number over a very large number, and that's practically 0. So if we looked at a, e to the x over x squared, e to the x is growing much quicker than x squared is, so it's not a. When we compare e to the x to the natural log of x, and again, picture the graphs of them as well. E to the x is growing a lot quicker than the natural log of x. But if we flipped it around, C turned out to be the correct answer, because in D, x is going to be greater than natural log of x, especially when you compare the graphs. And then E, 3 to the x, is going to increase greater than or quicker than 2 to the x. So here we're just looking at C. All right, for 26, what's going to help us out here is if we graph the function. So we have a piecewise function here. That we are just looking at y is equal to x for all x less than or equal to 0. And then x plus 1. So as we go from -2 to 1, so we're looking at this area right here. So even though we're not finding or using this area to help us with the integral, because it's not just of f of x, it's x times f of x, the graph can be helpful in helping us separate these, but it's not necessary. So we would say that the integral from -2 to 1 of x times f of x dx is that we could split this now, the integral from -2 to 0. So the function there, whenever x is less than or equal to 0, is going to be x. So we're going to get x times x, which is x squared dx, and then plus the integral from 0 to 1. So from 0 to 1, we're using this as f of x, so it's x times a quantity x plus 1 dx. And what we could do over here is just distribute. So we get the integral from -2 to 0 of x squared dx plus the integral from 0 to 1 of x squared plus x dx. And now we could just take the antiderivatives here. So I'm going to go down to where I have some more space. So now this becomes x cubed over 3 from x goes from -2 to 0 plus we'll have x cubed over 3 plus x squared over 2 from 0 to 1. Now we have to be careful here. The 0 is going to go first. So we're going to get 0 minus, now -2 will become a -8/3 plus, we'll put the 1 in first, so we'll get 1/3 plus 1/2, and then technically minus our 0 there. So we're going to get 8/3 plus 1/3 plus 1/2. So this gives us 9/3 or 3, 3 plus a half, so we're going to get 3.5 or 7/2, which is D. All right, so we're not getting into anything new or anything different today, but I do want to have you guys practice a free response question, and this is nice because parts of this are a good review for the Chapter 5 test. So please take a look at this, or you could go to the AP practice problems that I have in Classroom, and then you can look at this on your own. But go ahead, pause the video, try this problem on your own, and then come back to the video and see what the solutions are. All right, so pause the video if you need more time. But here the graph of a function f consists of a semicircle and two line segments as shown above. Let g be the function given by g of x is equal to the integral from 0 to x of f of t dt. So we could think of this as the graph of y equals f of x. And right away the connection is we may need the derivative of g. So I'm just going to write this out off to the side, but we're still going to need it in every explanation. But we would say g prime of x ends up equaling f of x. So we want to find g of 3. So g of 3 ends up being the integral from 0 to 3 of f of t dt, which is just the area under the curve. So if we're going from 0 over to 3 here, we have a quarter of a circle, and then we have a little triangle. But the triangle is shaded below the x-axis. So then the quarter of a circle formula is 1/4 pi r squared, so our radius is 2. And then we'll have minus the area of the triangle, which just measures 1 by 1 for the base and the height. So this will just give us 4 times 1/4, so we're just going to get pi minus 1/2. For b, find all values of x on the open interval -2 to 5, at which g has a relative maximum. Justify our answer. So I always like to start off with the explanation, and that kind of leads us into justifying. So we know g has a relative max when g prime of x, there's that big connection, which is equal to f of x, changes from positive to negative. Because when g prime of x changes from positive to negative, that means g is changing from increasing to decreasing, hence we would end up with a relative max. So if we look at the graph, where g prime of x or f of x changes from positive, so everywhere up here, f of x is positive, and it changes to negative right at 2. So we would say this happens at x equals 2. So that would probably be worth 2 points, maybe 2 points for A. For C, write an equation. So this is a little different. Write an equation for the line tangent to the graph of g at x equals 3. Well, right now we have our part of our point, 3 comma whatever. And then we need the slope of the tangent line at x equals 3, which means that's g prime of 3. So if we go back up to our graph, because g prime of 3 is really f of 3, and f of 3 is -1. So that's the slope of our tangent line. The ordered pair is really asking us for g of 3. Well, that's what we found in part A. That's pi minus 1/2. So then our equation, using point slope form, so I'm going to squeeze this in here, pi minus 1/2. So that becomes y minus y1, so y minus the quantity, pi minus 1/2, is equal to our slope, which is -1, times the quantity x minus x1, x minus 3. And we could leave it just like that. Question D. Find the x-coordinate of each point of inflection of the graph of g on the open interval from -2 to 5, and again, justify your answer. So we know we're going to have a point of inflection that occurs when g double prime of x, which is equal to f prime of x, changes signs. So now we're going back up to the graph and we're looking at the slopes of the tangent lines. So I'm going to do this in green. So when we first start, here's our tangent lines. All those slopes are positive till we get to a horizontal tangent line at x equals 0. So right now we would say f prime of x is positive. Then afterwards, all of our tangent lines have a negative slope. F prime of x is negative. Still from 2 to 3, they're still negative, but then they turn back to positive at 3. So we would say, based off of this, point of inflections occur when g double prime of x, which is equal to f prime of x, changes signs. So this is at x equals 0 and x equals 3. All right, guys, so very big announcement here. I'm pushing the test back another day. Tomorrow is going to be the tornado drill during third period. So that's going to cut into that class's test. So I will push everything back, give you guys an extra day to study. Hopefully that doesn't mess up anybody's schedule too much. But that Chapter 5 test will be Thursday. All right, so continue. If you need to go back and correct yesterday's homework assignment, please do. Here are some more problems from section 6.1. And then again, without a calculator, evaluate the integral for sine square x dx. And a hint here is to go back and look at 3 different versions of the cosine 2x identity. As always, guys, take care. Let me know if you have any questions.